Hello there, and welcome. Tonight we're going to explore one of the most mind-bending ideas in modern physics, the possibility that our entire universe might actually exist inside a black hole. Before we begin, I want you to get comfortable. This is a journey meant to help you relax and unwind. So find a cozy position, let your body settle, and allow your mind to drift along with these cosmic ideas. There's no need to remember everything or follow every detail perfectly. Just let the concepts wash over you like gentle waves. Tonight we're exploring the universe together, and whether you stay with me until the end or drift off to sleep along the way, that's exactly what this experience is meant for. Now, before you think this sounds like pure science fiction, I want you to know that serious scientists have genuinely considered this idea. It's a thought that challenges everything we think we know about reality, space, and time itself. But there's something deeply calming about contemplating the universe on such a grand scale. It puts everything into perspective, doesn't it? But before we begin, please take a moment to like and subscribe, but only if you enjoy what I'm doing here. Also, leave in the comments where you're tuning in from and what time it is there. It's great to see how these videos connect people from around the world. Now settle in, let your breathing slow, and let's take a gentle journey through space, time, and the nature of reality itself. What even is a black hole? Before we dive into the deep end, let's make sure we're all on the same page about what black holes actually are. You've probably heard of them. They're those cosmic monsters that swallow everything, right? Stars, planets, even light itself can't escape their grip. But what makes them so special? A black hole forms when a massive amount of matter gets compressed into an incredibly small space. Imagine taking something with the mass of our sun and squeezing it down to the size of a small city. The gravity becomes so intense that it warps the fabric of space and time around it. This creates what we call an event horizon, a boundary where the gravitational pull becomes so strong that nothing, not even light, can escape once it crosses that line. Think of space-time as a stretchy fabric, like a trampoline. When you place a bowling ball on a trampoline, it creates a dip. A black hole is like placing something infinitely heavy on that trampoline. It doesn't just create a dip. It punches a hole so deep that anything rolling toward it falls in and can never climb back out. At the center of a black hole, according to our current understanding, lies what physicists call a singularity. This is where all the matter that falls into the black hole gets crushed down to an infinitely small point with infinite density. Now that word infinite should make you a little uncomfortable, because in physics, infinities usually mean our theories are breaking down. They're signaling that something in our understanding isn't quite right. But here's where things get interesting. What happens inside a black hole? We can't see inside them, obviously, because no information can escape back out to us. So everything beyond that event horizon is, in some sense, hidden from the rest of the universe. It's like a cosmic curtain that blocks our view completely. Now, here's where our story really begins. In the 1970s, physicists started noticing something peculiar. When you write down the equations describing a black hole, specifically what's happening at its event horizon, they look strangely similar to equations describing the early universe. Isn't that odd? Two seemingly completely different phenomena, one describing a collapsed star and another describing the beginning of everything, sharing mathematical similarities. This observation planted a seed in the minds of several scientists. What if this similarity wasn't just a coincidence? What if there was a deeper connection between black holes and universes? The idea evolved over decades, but the basic concept is this. When we look at the Big Bang, we see the universe expanding from an incredibly hot, dense state. Everything started from what appears to be a singularity, that same problematic word we encountered with black holes. some scientists began asking, could our Big Bang actually be what's happening inside a black hole that exists in another, larger universe? Let me be clear here. This isn't mainstream physics. Most cosmologists don't think we're living inside a black hole, but it's a legitimate question that gets at real puzzles in our understanding of the universe, and some respectable physicists have explored the possibility seriously. The math that makes you think. Let's talk about why this idea isn't completely crazy. I promise to keep this as painless as possible. When Albert Einstein gave us general relativity in 1915, he provided a new way of understanding gravity. In his view, massive objects don't pull on each other through some mysterious force. Instead, they curve the space and time around them, and objects move along these curves. It's a bit like how a marble rolls along a curved surface. The equations of general relativity can describe many different scenarios, depending on what assumptions you make. One set of solutions describes what happens near a black hole. Another set describes an expanding universe. These are called the Friedmann equations, named after Alexander Friedmann, who developed them in the 1920s. Now here's the fascinating part. The mathematics of an expanding universe inside a black hole and the mathematics of our observed universe share some key features. Both involve space expanding. Both start from extremely high densities. Both contain matter and energy distributed in similar ways. In the 1970s and 1980s, several physicists, including notable figures like Raj Pathria, explored these mathematical parallels more carefully. They found that under certain conditions, you could describe a universe inside a black hole that looks remarkably like our own. But mathematics being similar doesn't mean the physics is the same, does it? After all, lots of different phenomena can be described by similar equations. That's fair. The real question is whether this mathematical similarity points to something deeper about reality, or whether it's just an interesting coincidence. What would it actually mean? Let's pause and really think about what we're proposing here. If our universe is inside a black hole, what would that actually entail? First, it would mean there's another universe outside ours, a parent universe, if you will. In that universe, our entire cosmos, everything we can see, all the galaxies, all the space between them, would be contained within what that universe perceives as a black hole. Maybe some advanced civilization in that parent universe looks at our black hole through their telescopes and sees it as just another collapsed star, completely unaware that inside it contains billions of galaxies, including the one where you're sitting right now reading this. Second, it would mean the Big Bang wasn't really the beginning of everything. Instead, it would be the moment when matter collapsed in that parent universe to form a black hole. From our perspective inside, this collapse appears as an expansion. We see everything moving apart because space itself is being created as the black hole forms. This is where it gets really weird. Time inside a black hole, according to general relativity, behaves strangely. An outside observer watching something fall into a black hole would see it slow down as it approaches the event horizon, never quite seeming to cross it. But from the perspective of the thing falling in, it crosses the horizon in a finite amount of time and keeps going. So from the outside universe's perspective, our universe might have formed in an instant, frozen at the moment of the black hole's creation. But from our perspective inside, billions of years have passed. Time itself is relative between the inside and outside of the black hole. Does this sound impossible? Well, time dilation is real. We've measured it. Clocks at different altitudes on Earth tick at different rates because of gravity. GPS satellites have to account for this or they wouldn't work. Inside a black hole, these effects become extreme. The observable evidence, or lack thereof. You might be thinking, this is all very interesting, but is there any way to actually test this idea? Can we find evidence that would tell us whether we're inside a black hole or not? This is where things get tricky. The honest answer is that it's extremely difficult, maybe impossible, to test directly. And that's a problem for this hypothesis, because science requires testable predictions. Think about it from our perspective. If we're inside a black hole, we're by definition cut off from the universe outside. No information can cross an event horizon from inside to outside. So we couldn't see or measure anything about that parent universe. It would be completely inaccessible to us. Similarly, the special conditions that would distinguish an inside a black hole universe from a not inside a black hole universe would have to show up in really subtle ways. The universe should look mostly the same from our perspective either way. That said, scientists have proposed some possible signatures we might look for. For instance, the way our universe expands and the distribution of matter and energy within it might carry some fingerprints of the black hole's properties. Some researchers have suggested that careful measurements of the cosmic microwave background, that leftover radiation from the early universe, might show patterns that could hint at a black hole origin. But here's the challenge. Any unusual pattern we find could be explained in multiple ways. Finding something weird doesn't automatically mean we're in a black hole. It might just mean our cosmological models need adjusting. As of now, we don't have compelling observational evidence that we're inside a black hole. Our universe looks pretty much like we'd expect an ordinary universe to look. But the absence of evidence isn't the same as evidence of absence, especially when we might not know what evidence to look for. Black holes. All the way down. Let's take this idea even further. If our universe could be inside a black hole in another universe, couldn't the black holes in our universe also contain universes? This is where things get properly mind-bending. Every time a star collapses and forms a black hole in our universe, could that be creating a new universe inside it? Could there be countless baby universes branching off from ours, each one developing its own galaxies, stars, and possibly even life? And if our universe is inside a black hole in a parent universe, maybe that parent universe is itself inside a black hole in another universe. Maybe it's black holes all the way up and all the way down, an infinite nested hierarchy of universes within universes. This isn't just wild speculation. Some physicists, like Lee Smolin, have seriously explored ideas like this in what's called cosmological natural selection. Smolin proposed that universes reproduce through black holes and that the fundamental constants of physics in each baby universe might be slightly different from its parent. Over time, this could lead to an evolution of universes, where the ones that produce the most black holes become most common. It's a fascinating idea, though it's fair to say it remains highly speculative. The challenge is that it's very difficult to test. How would you verify that black holes contain universes when you can't look inside them? How would you confirm that our universe is part of this cosmic family tree? But let's be honest, the sheer elegance of the idea is appealing. It would mean that what appears to us as destruction, a star collapsing into a black hole, is actually creation from another perspective. Every ending is a beginning. What general relativity actually tells us? We should take a moment to dig a bit deeper into what Einstein's equations really say about all this. General relativity is our best theory of gravity and space-time, and any discussion of black holes and universe origins has to grapple with it. The equations of general relativity are notoriously difficult to solve. They involve complex mathematics describing how matter and energy curve space-time, and how that curved space-time tells matter and energy how to move. It's a feedback loop that creates incredibly rich behavior. One of the most famous solutions to these equations is called the Schwarzschild solution, which describes the space-time around a non-rotating black hole. This solution contains a singularity at the center and an event horizon at a certain radius. What's crucial is that the Schwarzschild solution describes the space-time outside the black hole fairly well, but the interior, inside the event horizon, is more problematic. Inside the event horizon, according to the equations, space and time swap roles in a certain mathematical sense. The direction toward the singularity becomes more like a direction in time than in space. This means that falling toward the singularity isn't just a matter of turning around, it's as impossible as travelling backward in time. The singularity isn't just a place you reach, it's a moment in your future that you inevitably encounter. Now, when physicists tried to match this interior solution with a cosmological model, a description of an expanding universe, they found that under certain conditions, you could glue them together mathematically. The interior of a black hole in some solutions can look like an expanding universe. But there's a catch, and it's a big one. The interior of a typical black hole doesn't expand forever. According to the classical solutions, everything inside is doomed to hit the singularity in a finite amount of time. Our universe, on the other hand, has been expanding for about 13.8 billion years and shows no signs of imminent collapse into a singularity. How do you reconcile this? Some proposed solutions involve black holes that are still forming, not yet fully collapsed, or black holes with special properties that allow for more stable interiors. These are called regular black holes, or black holes with different kinds of matter inside them. But these solutions often require conditions that might not exist in nature, or at least haven't been observed. Quantum gravity, the missing piece. Here's the thing, we're not entirely sure what happens inside a black hole because our theories break down. General relativity predicts that singularity, that point of infinite density, but most physicists don't think infinities are real physical things. They're signals that our theory is incomplete. What's missing? Quantum mechanics. Einstein's general relativity is a classical theory. It works brilliantly for large-scale phenomena, but it doesn't account for the quantum nature of reality that dominates at incredibly small scales. And inside a black hole, especially near the singularity, we're dealing with both extreme gravity and quantum scale distances. We need a theory of quantum gravity, a framework that unifies general relativity with quantum mechanics. We don't have one yet. String theory and loop quantum gravity are leading candidates, but neither is complete or fully tested. What does quantum gravity tell us about black hole interiors? We don't know for sure, but there are hints. Some approaches suggest that singularities might not form at all. Instead, quantum effects might cause something different to happen. Maybe a bounce where the collapsing matter rebounds and starts expanding again. This is where the connection to cosmology becomes really interesting. If quantum effects cause a bounce inside a black hole, you could genuinely have a situation where the interior evolves into something resembling a universe. The Big Bang, from this perspective, might be the quantum bounce that happened at the center of a black hole in another universe. This is the essence of some modern proposals, like those explored by physicists Nikodem Popowski and others. They use modifications of general relativity that include quantum-like effects and show that black holes can indeed give birth to expanding universes on the inside. Is this proven? No, not even close. But it's an active area of research, and it shows that the idea isn't as far-fetched as it might initially sound. The horizon problem and inflation. Let's shift gears and talk about some of the actual problems in cosmology that this universe in a black hole idea might address. One of the biggest puzzles about our universe is called the horizon problem. When we look at the cosmic microwave background, the afterglow of the Big Bang, we see that it's incredibly uniform. The temperature is almost exactly the same in every direction, varying by only about 1 part in 100,000. This is weird because according to standard Big Bang cosmology, regions on opposite sides of the sky have never been in contact with each other. They're too far apart. Light hasn't had time to travel between them since the beginning of the universe. So how did they end up at the same temperature? If they were never in contact, how did they know to have the same properties? It's like finding that people on opposite sides of the Earth, who have never communicated, are all wearing identical outfits. How would that happen? The standard solution to this problem is called inflation. The idea, developed by Alan Guth and others in the 1980s, is that the universe underwent a period of incredibly rapid expansion in its first fraction of a second. Before inflation, all the regions we can see today were in contact, allowing them to reach the same temperature. Then inflation stretched them apart so rapidly that they ended up far apart by the time the universe settled into its more sedate expansion. Inflation works well and explains several features of our universe, but it requires some special conditions and a hypothetical field called the inflaton. We've never directly detected an inflaton, and there are debates about whether inflation really happened. Now here's where the black hole hypothesis comes in. If our universe formed inside a black hole, the initial conditions might naturally be uniform, because they all came from the same collapsing matter in the parent universe. You wouldn't need inflation to explain the uniformity. Everything started out in close contact before the black hole formed, so of course it all has similar properties. This is appealing because it removes the need for inflation's special conditions, but it's not without problems of its own. You still need to explain exactly how the collapse in the parent universe translates to the expansion we see, and whether that process would really produce the specific patterns we observe. Dark energy and the accelerating universe. There's another big mystery in cosmology that just might connect to this idea. Dark energy. In the late 1990s, astronomers discovered something shocking. The expansion of the universe isn't slowing down, as everyone expected. It's speeding up. Galaxies are moving apart from each other, faster and faster, as time goes on. This acceleration requires some kind of energy that pushes space apart. We call it dark energy, and it makes up about 68% of the total energy content of the universe. But we have no idea what it actually is. The simplest explanation is that it's a property of space itself, a cosmological constant that Einstein once introduced and later called his biggest blunder. But we don't know why it has the value it does, and that value is very strange. It's much smaller than theoretical predictions suggest it should be. Could dark energy be related to our universe being inside a black hole? Some researchers have speculated that it might be. The expansion of space inside the black hole might be driven by the properties of the black hole itself, its mass, rotation, and charge. From our perspective inside, this manifests as dark energy pushing the universe apart. This is highly speculative, and I want to be clear that most experts don't think this is the answer to dark energy, but it illustrates how the universe in a black hole idea could potentially address real problems in cosmology. The challenge, as always, is making specific predictions that could be tested. It's not enough to say maybe dark energy is caused by black hole properties. You need to calculate what those properties would have to be, what observable consequences they would have, and then check whether observations match. So far, no one has made a compelling case that passes those tests. The multiverse connection. This whole discussion naturally leads us to the concept of the multiverse. If our universe could be inside a black hole, and if black holes in our universe might contain other universes, then we're talking about a vast ensemble of universes, a multiverse. The multiverse isn't a single idea. It's actually several different concepts that sometimes get lumped together. There's the quantum multiverse arising from the many worlds interpretation of quantum mechanics. There's the inflationary multiverse, where different regions of space inflate by different amounts and develop different properties. And there's the black hole multiverse we've been discussing. Some physicists love the multiverse concept. It provides potential explanations for why our universe has the properties it does. If there are countless universes with different properties, then of course we find ourselves in one that can support life. We couldn't exist in the others. This is called the anthropic principle. Other physicists hate it. The worry is that the multiverse is unfalsifiable. If we can never observe these other universes, if they're forever beyond our reach, then how is this science rather than philosophy? Science requires testable predictions, and if a theory makes no predictions that can be checked, what good is it? This is a legitimate concern. The black hole multiverse faces the same challenge. Even if it's true, it might be impossible to prove. We're stuck inside our black hole with no way to peek outside or confirm that other universes exist in other black holes. But some argue that's too strict a criterion. Many theories in physics involve things we can't directly observe. We can't see inside atoms, but we infer their structure from experiments. We can't visit the early universe, but we study its remnant radiation. Maybe we can find indirect evidence for a multiverse, even if we can't visit other universes directly. The debate continues, and it gets at deep questions about what science is and what kinds of explanations we should accept. Information paradox and black holes. We need to talk about one of the most important problems in theoretical physics, the black hole information paradox. This is directly relevant to our discussion, and it reveals deep tensions in our understanding of reality. Here's the problem. According to quantum mechanics, information cannot be destroyed. If you know the complete quantum state of a system at one time, you can in principle work backward or forwards to find its state at any other time. Information is conserved. But according to classical general relativity, when something falls into a black hole, it disappears behind the event horizon, and all information about it is lost to the outside universe. Eventually, the black hole will evaporate through Hawking radiation, a quantum process discovered by Stephen Hawking in the 1970s. When the black hole finally disappears, all the information that fell into it seems to be gone forever. That's a problem. We have two of our best theories, quantum mechanics and general relativity, giving contradictory answers about what happens to information. One says it's conserved, the other says it's destroyed. This paradox has occupied some of the best minds in physics for decades. Proposed solutions include the idea that information is somehow encoded on the event horizon and released back out through Hawking radiation, or that black holes don't fully evaporate but leave behind remnants containing the information, or that space-time itself has some kind of fuzziness that prevents information from truly being lost. How does this relate to our universe being inside a black hole? Well, if universes exist inside black holes, what happens to all the information in those universes? From the outside, the black hole eventually evaporates. Does that mean entire universes with all their galaxies and stars and possibly civilizations just disappear? Or does the information somehow escape? Some proposals suggest that information might tunnel out of the black hole through quantum effects, or that baby universes might permanently separate from their parent universe, taking their information with them. These are deep waters, and there are no clear answers yet. The information paradox reminds us that black holes are not well understood at a fundamental level. Until we resolve these quantum puzzles, we can't be confident about what really happens inside them, or whether they could truly contain universes. What observations tell us about our universe? Let's ground ourselves in what we actually know about our universe through observation. Whatever theory we entertain, whether we're in a black hole or not, needs to match these observations. Our universe is expanding. This is established beyond doubt. Galaxies are moving away from us, and the farther away they are, the faster they're receding. This relationship was first discovered by Edwin Hubble in the 1920s. The universe appears to be flat, or very nearly so. By flat, I mean the large-scale geometry of space follows the rules of Euclidean geometry you learned in school. Parallel lines stay parallel, Angles in a triangle add up to 180 degrees. Measurements of the cosmic microwave background confirm this to high precision. The universe contains dark matter. We can't see it directly, but we observe its gravitational effects on galaxies and galaxy clusters. It makes up about 27% of the universe's total mass energy. The universe contains dark energy, as we discussed, about 68% of the universe's mass energy. The remaining 5% is ordinary matter, the stuff that makes up stars, planets, and us. The universe has a very specific pattern of tiny temperature fluctuations in the cosmic microwave background. These fluctuations are the seeds that grew into galaxies and large-scale structures. Their statistical properties match predictions from inflation remarkably well. The universe has the right balance of light elements, hydrogen, helium, and a bit of lithium, that were forged in the first few minutes after the Big Bang. The amounts we observe match theoretical predictions extremely well. Now, all of these observations are consistent with the standard model of cosmology. They don't require us to be inside a black hole to explain them. The universe in a black hole hypothesis needs to account for all of these features, and it's not clear that it does so as naturally or precisely as the standard model. This is one reason why the idea remains on the fringe. It's not that it's impossible, but it doesn't seem to offer clear advantages over existing explanations, and it introduces new complications. The philosophy of unknowability. There's a philosophical dimension to all of this that's worth exploring. If we are inside a black hole with no possible way to observe the universe outside, what does that mean for knowledge and reality? In science, we're generally comfortable with the idea that there are things we don't know yet but might discover later. We didn't know about the cosmic microwave background until 1965. We didn't know about the accelerating expansion until 1998, but these unknowns were eventually revealed through better observations. But what about things that are unknowable in principle? If we're truly cut off from any information about a parent universe, then no future experiment, no matter how clever, could reveal it to us. Is that still science? Some philosophers argue that such questions fall outside the realm of science into metaphysics. If a proposition can't be tested even in principle, then it's not a scientific question, even if it uses scientific language and concepts. Others argue that this is too narrow. Scientific reasoning can take us to conclusions about unobservable things, if those conclusions are necessary to explain what we do observe. For instance, we can't directly observe what happened before the cosmic microwave background was emitted, but we can infer it. Maybe we could infer a parent universe the same way. There's also something unsettling about the idea that the fundamental nature of reality might be unknowable to us. Humans like to think we can understand the universe through reason and observation. The possibility that we're fundamentally limited, that there are truths we can never access, is humbling and perhaps disturbing. But maybe that's the nature of reality. Maybe we have to accept that there are limits to knowledge, or maybe we'll find a clever way around those limits. The history of science is full of seemingly impossible problems that eventually yielded to human ingenuity, alternative ideas, and competing theories. To be fair, we should acknowledge that we're inside a black hole is just one of many speculative ideas about the nature of the universe. It's not even the most popular one among physicists. Let's briefly survey some alternatives. The standard model of cosmology, often called lambda CDM, doesn't require us to be inside a black hole. It describes the universe as arising from a Big Bang, going through a period of inflation, then expanding and cooling to form the structures we see today. This model has been remarkably successful at matching observations. Some physicists favour cyclic universe models, where the universe goes through endless cycles of expansion and contraction. Each big crunch leads to a new Big Bang. These models have their own challenges but avoid the question of what came before the Big Bang by making the universe eternal. Others explore models based on string theory, which posits that fundamental particles are actually tiny vibrating strings. String theory naturally produces extra dimensions beyond the 3 spatial dimensions we experience. Maybe our universe is a 3-dimensional slice of a higher dimensional reality, a concept called brain-world cosmology. There are also quantum cosmology models that try to describe the universe's origin using quantum mechanics directly, treating the universe itself as a quantum object. These models sometimes eliminate the initial singularity entirely, replacing it with a quantum state with no defined beginning. Each of these ideas has strengths and weaknesses. The honest truth is that we don't know which, if any, is correct. The origin and fundamental nature of the universe remain open questions. The universe in a black hole idea is interesting because it connects 2 seemingly separate mysteries: the nature of black holes and the origin of the universe. If it were true, it would reveal a beautiful symmetry in nature. But beauty and truth don't always align, and we need evidence, not just elegance, to make progress. Could we ever know for sure? So, after all this discussion, where does that leave us? Could we ever definitively determine whether we're inside a black hole? In principle, there might be ways. If the properties of our universe bore very specific signatures that could only be explained by a black hole origin, that would be compelling evidence. For example, if we discovered that the fundamental constants of nature, or the patterns in the cosmic microwave background, had features that exactly matched predictions from black hole physics, that would be telling. Some researchers have proposed that we might detect gravitational wave signatures from the formation of the black hole that contains us. These would be imprinted in the large-scale structure of the universe. But this is highly speculative, and no one has made a convincing case that such signatures would be detectable or distinguishable from other phenomena. Another possibility is that advances in quantum gravity might allow us to make precise predictions about what should happen inside black holes, and we could check whether our universe matches those predictions. If string theory or loop quantum gravity reaches a point where it makes clear, testable statements about black hole interiors, we could compare those to cosmological observations. But there's a real possibility that this question is simply unanswerable. If the universe inside a black hole looks exactly like a universe not inside a black hole, then there's no measurement we could make that would tell them apart. And if that's the case, does the question even matter? This gets back to the philosophy of science. Some would say that if 2 theories make identical predictions about everything we can observe, then they're effectively the same theory, just expressed differently. The distinction between them is meaningless. Others would say that there's still an objective truth about which one is correct, even if we can never know it. I'm not sure there's a definitive answer to that philosophical question, but practically speaking, if we can't test it, it's hard to call it science. The bigger picture. Why this matters? You might be wondering, even if this is an interesting thought experiment, does it actually matter? What difference does it make to our daily lives, or even to working scientists, whether we're in a black hole or not? That's a fair question. On a practical level, it probably doesn't matter much. Whether our universe originated in a black hole or through some other mechanism, the physics we observe remains the same. Stars still shine, atoms still bond, and your coffee still cools down if you leave it sitting too long. But on a deeper level, questions like this matter because they're about understanding the nature of reality itself. Humans have always looked up at the sky and wondered where we came from, where we're going, and what our place is in the cosmos. These are fundamental questions that drive scientific inquiry. Moreover, even speculative ideas can lead to real progress. The attempt to understand black hole interiors has driven advances in quantum gravity and theoretical physics. The connections between black holes and thermodynamics led to insights about information and entropy that have applications beyond black holes. Sometimes pursuing a wild idea leads you somewhere unexpected and valuable. There's also something profound about the possibility that the most destructive phenomenon we know of, a black hole, might also be creative, birthing entire universes. It speaks to a kind of cosmic recycling, where nothing is truly destroyed but instead transforms into something new. Whether or not it's literally true, there's a poetic resonance to that idea. And finally, considering possibilities like this reminds us of how much we don't know. It's easy to fall into the trap of thinking we've figured out most of the big questions. We haven't. The universe is far stranger than we imagine, and maybe stranger than we can imagine. Staying open to radical ideas while demanding rigorous evidence is how science makes progress. The limits of human understanding. As we near the end of our journey, it's worth reflecting on the limits of human understanding. Our brains evolved to understand medium-sized objects moving at everyday speeds in 3 dimensions. We're good at that because it kept our ancestors alive. But the universe operates on scales and in regimes far removed from everyday experience. The quantum realm, where particles exist in superposition and can be entangled across vast distances. The relativistic realm, where time slows down and space contracts. The cosmological realm, dealing with billions of light years and billions of years. We've extended our understanding into these alien territories through mathematics and careful experimentation. But there may be limits to how far intuition can carry us. Maybe the true nature of black hole interiors is something our brains simply can't visualize or understand in any intuitive sense. We might be able to describe it mathematically, but not truly comprehend it. This is already somewhat true. Physicists work with quantum mechanics very successfully, but if you ask them what's really happening at the quantum level, you'll get different answers depending on whom you ask. The math works, we can make predictions, but the underlying reality remains mysterious. Black holes and the origin of the universe push us even further into this territory. We're dealing with extremes of gravity, density, and energy that have no parallels in our experience. The fact that we can even ask coherent questions about these things is remarkable. Whether we can answer them is another matter. But humans are remarkably creative. We've invented new mathematical tools, developed new technologies, and expanded our understanding in ways our ancestors could never have imagined. We went from thinking the Earth was flat and at the center of everything to understanding that we're on a small planet, orbiting an average star in a typical galaxy among billions. Who knows what we might discover next? Living with uncertainty. Here's something I think is important to sit with. We don't know. We don't know if we're in a black hole. We don't know exactly how the universe began. We don't know what dark matter and dark energy are. We don't know how to unify quantum mechanics and gravity. We don't even know if we're asking the right questions. Science is often presented as a collection of answers, of facts and certainties. And there are many things we do know with high confidence. But at the frontier of knowledge, science is really about uncertainty, about probabilities and possibilities, about the next question rather than the final answer. Are we inside a giant black hole? Maybe. The idea isn't completely crazy. There are mathematical reasons to take it seriously, and some legitimate scientists have explored it. But there's no strong evidence for it, and significant challenges remain. Most physicists would say it's unlikely, but not impossible. And you know what? That's okay. Not knowing is okay. It's actually exciting. It means there are still discoveries to be made, still mysteries to unravel. It means the universe can still surprise us. If we definitively prove tomorrow that we are inside a black hole, that would be astonishing. It would reshape our understanding of cosmology and raise countless new questions. What is the parent universe like? How many other black hole universes are there? Could we ever communicate with them? If we definitively proved we're not in a black hole, that would be fine too. It would narrow down the possibilities and point us toward other explanations for the universe's origin and properties. Either way, we learn something. The journey of understanding is ongoing. We're not at the end. We might never reach the end. And perhaps that's as it should be. A universe fully understood might be a universe without wonder. So let's come back to our original question. What if we're inside a giant black hole? What would that mean for us, for our place in the universe, for the nature of reality itself? If it's true, it would mean our cosmic story is even stranger and more layered than we thought. It would mean the Big Bang was a kind of illusion, a perspective from inside a collapsing object in another realm. It would mean there might be a vast network of universes, nested like cosmic Russian dolls, each one containing black holes that birth new universes. It would also mean we're fundamentally isolated from any larger reality that might exist. We're like characters in a book, unable to peek beyond the pages that contain our story. But here's the thing, even if we're not in a black hole, we're still pretty isolated. The observable universe, the part we can see, is limited by the speed of light and the age of the universe. There are galaxies so far away that their light will never reach us because space is expanding too fast. In a sense, we're already cut off from most of reality, black hole or not. What matters is that we keep asking questions. We keep looking up at the stars and wondering. We keep pushing the boundaries of knowledge, even when those boundaries seem impossibly far away. The question of whether we're in a black hole connects to so many fundamental issues in physics. The nature of space-time, the beginning of the universe, the quantum properties of gravity, the fate of information. Working on these problems, even if we never fully solve them, teaches us about how reality works. It reveals patterns and principles that apply elsewhere. It trains our minds to think in new ways. And who knows, maybe some kid watching this video right now will grow up to be the physicist who finally cracks the puzzle of quantum gravity. Maybe they'll discover the missing piece that tells us definitively whether universes can exist inside black holes. Maybe they'll find something even more amazing that we haven't even thought to ask about yet. What this tells us about science. I want to zoom out for a moment and talk about what this whole discussion reveals about how science actually works, because I think there are some misconceptions worth addressing. Science isn't about being certain, it's about being curious. It's about following evidence wherever it leads, even if it leads somewhere strange. It's about being willing to change your mind when new data comes in. The "are we in a black hole" question is science at its most exploratory. It's not settled science, not by a long shot. It's not even mainstream science, but it's real scientists doing real work, using real mathematics and physics to explore a possibility. They're not claiming it's true. They're asking whether it could be true. And if so, what would that look like? This is how progress happens. You entertain ideas, you work through the implications, you try to find ways to test them. Most ideas fail. That's okay. The ones that survive rigorous scrutiny become part of our accepted understanding, at least until something better comes along. Einstein's relativity was crazy when he first proposed it. The Big Bang was considered absurd by many scientists in the mid-20th century. Plate tectonics was dismissed for decades. Now these ideas are fundamental to our understanding of the universe. They survived because they made predictions that were confirmed by observation. The black hole universe idea is still in the entertaining possibilities stage. It hasn't made unique, testable predictions that have been confirmed. Maybe it never will, but the process of exploring it is valuable in itself. And here's something else. Science is a human endeavor. It's done by people with hunches and intuitions, with aesthetic preferences and philosophical biases. Scientists aren't emotionless logic machines. They're creative, passionate people who are drawn to certain ideas and repelled by others. Some physicists love the elegance of the black hole universe connection. Others find it too speculative. Some think it's a distraction from more productive research. Others think it might be the key to understanding quantum gravity. All of these perspectives are valid. Science progresses through this kind of diversity of thought. What keeps science on track is the requirement for evidence. You can have whatever hunches you want, but ultimately, your ideas have to make contact with reality. They have to predict something that can be observed and measured. If they don't, they might be interesting philosophy or mathematics, but they're not quite science. The practical universe. Let's talk about something that might seem mundane after all this cosmic speculation. The universe we actually live in, day to day. Whether or not we're in a black hole, you still wake up in the morning. The sun still rises, water still boils at 100 degrees Celsius at sea level. Gravity still pulls things downward. The chemistry that powers your body still works the same way. All the physics we use in everyday life, in technology, in medicine, none of that changes based on cosmological theories about the universe's origin. General relativity is used in GPS satellites. Quantum mechanics is used in computer chips and medical imaging. These theories work fantastically well for their intended purposes, regardless of what's happening at the cosmic scale. This is actually an important point. Science operates at different scales, and what's true at one scale doesn't always directly affect what's true at another. The quantum weirdness of individual particles doesn't make large objects behave weirdly. The expansion of the universe doesn't make galaxies expand, or solar systems, or atoms. Gravity works the same way in a lab, whether the universe is inside a black hole or not. So in a practical sense, the answer to our question doesn't impact most of science or everyday life. But in a philosophical and scientific sense, it matters because it's about understanding the complete picture, not just the parts we directly interact with. It's like asking where the ocean came from while you're swimming in it. The answer doesn't change how you swim, but it tells you something important about the world you're swimming in. Future observations and discoveries. Looking ahead, what might help us answer this question? What observations or discoveries could make a difference? First, any breakthrough in quantum gravity would be enormous. If we develop a working theory that successfully unifies general relativity and quantum mechanics, it should tell us what happens inside black holes. It should describe the singularity, or whatever replaces it, and it should tell us whether universes can exist inside. This is probably the most important piece of the puzzle. Several approaches are being pursued. String theory is one. Loop quantum gravity is another. There are others like causal set theory, asymptotic safety, and various approaches to emergent gravity. None has achieved the status of a confirmed theory yet, but progress is being made. Second, more precise observations of the cosmic microwave background and the large-scale structure of the universe might reveal subtle patterns that could distinguish between different cosmological models. We've already learned an enormous amount from these observations, and future experiments will be even more sensitive. Third, gravitational wave astronomy is a new field that's just getting started. The detection of gravitational waves from merging black holes and neutron stars opened a new window on the universe. As we detect more events and with greater precision, we might learn things about black holes that are currently hidden from us. Fourth, theoretical work continues on understanding black hole thermodynamics, the information paradox, and the connections between black holes and quantum information. Insights from these areas might unexpectedly illuminate questions about cosmology. And fifth, sometimes the answer comes from a direction you didn't expect. The discovery of dark energy came from observations of distant supernovae, not from theoretical predictions. The cosmic microwave background was discovered by accident. Sometimes you find what you're not looking for. The point is, we're not stuck. Science continues to advance. We're asking better questions and developing better tools to answer them. Whatever the truth is about our universe, we're likely to understand it better in the coming decades than we do now. The emotional dimension. I want to talk about something that doesn't get discussed much in science videos: how all of this makes us feel. Does it make you uncomfortable to think we might be inside a black hole? Does it make you feel small, or insignificant, or isolated? Or does it make you feel part of something larger, connected to a cosmic web of universes? These reactions are worth paying attention to. Our emotional responses to ideas often tell us something important about ourselves, even if they don't tell us whether the ideas are true. For some people, the thought that our universe might be contained within a black hole is claustrophobic. It feels like being trapped, cut off from something larger. The idea that there might be a parent universe we can never observe or reach can feel limiting. For others, it's strangely comforting. It suggests that even in destruction, there's creation. That the universe is more layered and rich than it appears. That what looks like an end might be a beginning from another perspective. And for others still, it simply doesn't provoke much emotion at all. It's an interesting intellectual puzzle, but it doesn't feel personal. All of these reactions are valid. Science deals with facts and evidence, but how we feel about those facts is part of the human experience of understanding the universe. Personally, I find something beautiful in the idea, even if I'm not convinced it's true. The notion that black holes, these objects we think of as destroyers, might actually be creative forces giving birth to entire universes, appeals to me. It suggests a kind of cosmic balance, a recycling of existence on the grandest possible scale. But I also appreciate the mystery. Not knowing is uncomfortable sometimes, but it's also exhilarating. It means there's still room for wonder, still discoveries waiting to be made. If we knew everything, what would be the point? Other minds, other perspectives. Here's a thought that connects to our topic. If our universe is inside a black hole in another universe, could there be intelligent beings in that parent universe? And if so, what would they make of our black hole? From their perspective, if they could observe it at all, it would just be a black hole. A region of space-time where something collapsed. They probably wouldn't suspect that inside it, entire galaxies are forming, stars are being born and dying, and on at least one small planet, beings are asking questions about the nature of reality. This is a profound kind of isolation. Not just that we can't see out, but that they can't see in. Two realms of consciousness, potentially, completely unable to communicate or even know about each other. But flip it around. In our universe, we've detected or inferred the existence of millions of black holes. Could each one contain a universe? Could each one harbour galaxies, stars, planets, and possibly life? Could there be civilizations inside those black holes, asking the same questions we're asking? If so, then the universe, or multiverse, would be teeming with life. But each isolated in its own pocket of reality. It's a strange mixture of abundance and loneliness. Of course, this is pure speculation layered on speculation. We don't know if universes exist in black holes. We don't know if intelligent life exists elsewhere in our universe, let alone in hypothetical other universes. But the possibility is worth contemplating because it shapes how we think about our place in the cosmos. Are we alone? Maybe not in the sense we usually ask that question. Maybe there are countless other civilizations, but forever unreachable, forever unknowable. That's a different kind of aloneness, but it's still aloneness. Or maybe we're not in a black hole, and the universe is a simpler place than all this suggests. Maybe other civilizations are out there in our universe, potentially reachable if we could just figure out how to travel between the stars. That's a more hopeful vision in some ways. The role of mathematics. Throughout this discussion, I've mentioned mathematics repeatedly. It's worth pausing to appreciate what an extraordinary tool mathematics is for understanding reality. Mathematics is a language we invented to describe patterns, relationships, and structures. It's abstract, built from pure logic. Yet somehow this invented language turns out to be incredibly effective at describing the physical world. Why should that be? Why should the universe care about our mathematical equations? This is actually a deep mystery that physicists and philosophers have pondered. Eugene Wigner famously called it the unreasonable effectiveness of mathematics in the natural sciences. When we talk about universes inside black holes, we're really talking about solutions to mathematical equations, Einstein's field equations in particular. These equations relate the curvature of spacetime to the distribution of matter and energy. They're beautiful, elegant, and they've been confirmed by countless experiments. But here's the thing. The equations have many solutions. Each solution describes a possible universe, a possible configuration of spacetime. The Schwarzschild solution describes a black hole. The Friedmann-Lemaitre-Robertson-Walker solution describes an expanding universe. And it turns out you can construct solutions that have properties of both. So mathematically, a universe inside a black hole is possible. The equations allow it, but mathematics allowing something doesn't mean nature uses it. The equations of general relativity also allow for wormholes, shortcuts through spacetime. But we've never observed a wormhole, and most physicists think they probably can't form naturally, even though the math permits them. The question is always, which mathematical solutions correspond to physical reality? That's where observation comes in. We can explore the landscape of mathematical possibilities, but only experiment and observation can tell us where in that landscape we actually live. This is why the "are we in a black hole" question is so tricky. The math says maybe. Observation doesn't clearly say yes or no. We're left in uncertainty, and mathematics alone can't resolve it. Time, existence, and identity. Let's get a bit philosophical for a moment. If our universe is inside a black hole, what does that mean for time? Time is strange inside a black hole. As I mentioned earlier, space and time swap roles in a certain sense. The singularity isn't just somewhere you could go. It's someone you will reach. It's in your future, unavoidably. But our universe has been around for 13.8 billion years. We're clearly not immediately hitting a singularity. How does that work? One possibility is that from the perspective of the parent universe, no time has passed at all. We talked about time dilation earlier, time running at different rates in different gravitational fields. The extreme case is at the event horizon of a black hole, where time appears to stop completely from an outside perspective. So maybe the entire 13.8 billion year history of our universe, from our perspective, corresponds to essentially zero time in the parent universe. Our Big Bang, the formation of galaxies, the evolution of life, everything that's happened, all of it might be frozen at a single moment from another point of view. This is deeply weird. It challenges our sense of what it means to exist, to have a history, to be real. If no time has passed in the real universe outside, are we even real? Or are we just a mathematical possibility, played out in slow motion inside a black hole? But here's the thing. Our experience of time is real to us. The passage of time, the flow from past to future, the accumulation of memories and experiences, that's our reality. Whether it looks different from another perspective doesn't make it less real. This is similar to debates about the reality of quantum states, or the reality of distant galaxies we can't interact with. Different frameworks give different descriptions of reality, but what we experience is what matters for us. Still, it's a humbling thought. The entirety of human history, every triumph and tragedy, every person who's ever lived, all of it might be, from another point of view, essentially instantaneous. A flash of possibility inside a collapsing object. We think we're living out a grand cosmic drama spanning billions of years, and maybe we are, but maybe to someone else, we barely exist at all. The question of why we've spent a lot of time on the question of whether we're in a black hole and how that could work. But there's another question lurking beneath it all. Why? Why would the universe be structured this way? If it's true that black holes create universes, why? What purpose does it serve? Or is there no purpose at all? Is it just a consequence of physics, no more meaningful than water flowing downhill? Science is very good at answering how questions. How does gravity work? How did stars form? How does evolution produce complex life? These are questions about mechanisms, about processes, about the rules that govern cause and effect. Science is less comfortable with why questions, especially the deep ones. Why do these laws of physics apply rather than some other laws? Why is there something rather than nothing? Why does the universe exist at all? Some scientists would say these questions are outside the scope of science, that they're philosophical or theological rather than scientific. Science can tell you how things work, but it can't tell you why they work that way at the most fundamental level. It can't give you meaning or purpose. It can only describe what is. Others argue that science can address at least some why questions by showing that certain features of the universe are necessary consequences of deeper principles. For instance, we might ask why the speed of light is constant in all reference frames. The answer from relativity is that space and time are unified into space-time, and the constant speed of light falls out of that geometry. The why reduces to a how at a deeper level, but eventually you hit bedrock. Why are the laws of physics the way they are? Why does mathematics describe reality? Why does anything exist? Science doesn't have answers to these ultimate questions, and maybe it never will. If we are inside a black hole, that doesn't really answer the why question. It just pushes it back a level. Okay, our universe formed from a black hole in another universe, but why does that universe exist? And where did it come from? Maybe the answer is an infinite regress, universes within universes, black holes all the way down, with no ultimate beginning. Maybe the answer is circular, universes creating universes in a self-sustaining loop. Or maybe there is an ultimate answer that we're just not capable of grasping yet. Living in the unknown. We're approaching the end of our journey, and I want to leave you with some thoughts about living with uncertainty and mystery. The honest truth is that we don't know if we're in a black hole. We don't know how the universe began. We don't know what most of the universe is made of. We don't know if we're alone. We don't know what consciousness is or why we have subjective experiences. These unknowns can be uncomfortable. Humans like certainty. We like clear answers. We like to feel that we understand our place in the world. But maybe there's another way to look at it. Maybe the unknowns are what make life interesting. Maybe the mystery is what drives us forward. Maybe not knowing is an invitation to keep exploring, keep questioning, keep learning. Every answer we find leads to new questions. When we discovered that the universe is expanding, that led to questions about dark energy. When we found the cosmic microwave background, that led to questions about inflation. When we detected gravitational waves, that opened up a whole new way of observing the universe. The "are we in a black hole" question, whether answered or not, has already led to valuable insights about quantum gravity, black hole thermodynamics, and cosmology. The journey matters, not just the destination, and personally, I find it exciting that there are still fundamental questions about reality that we don't know the answers to. It means we're not done. It means there's still room for discovery. It means someone watching this video right now might be the person who makes the breakthrough that changes everything. The universe is under no obligation to make sense to us. It doesn't have to fit our intuitions or our preferences. It's what it is, whatever that turns out to be. Our job is to observe it as carefully as we can, think about it as clearly as we can, and try to understand it as deeply as we can. Sometimes that means accepting uncertainty. Sometimes it means holding multiple possibilities in mind at once. Sometimes it means saying, "I don't know," and being okay with that. So are we inside a giant black hole? Maybe. The idea isn't crazy. The mathematics allows for it. Some serious physicists have explored the possibility, but we don't have compelling evidence for it, and we may never know for sure. What we do have is a universe that's stranger and more wonderful than most of us imagine. Whether it's inside a black hole or not, it's a place where stars fuse hydrogen into helium, where galaxies collide and merge, where life emerged from chemistry and became complex enough to ask questions about its own origin. We live on a small planet orbiting an average star in the outer suburbs of a typical galaxy. We're made of atoms that were forged in the hearts of ancient stars that exploded billions of years ago. We're the universe's way of knowing itself. As Carl Sagan memorably put it, does it matter if all of this is happening inside a black hole? On one level, no. The stars still shine, life still flourishes, love, joy, curiosity, wonder, all the things that make existence meaningful, they're all still real. On another level, yes. It matters because understanding reality, even the parts we can't directly observe, is part of what makes us human. We're the species that looks up at the stars and asks why. We're the species that builds telescopes and particle accelerators and space probes to explore the unknown. We're the species that writes equations on blackboards and builds computer models and debates theories late into the night. Whether we're in a black hole or not, we're part of something larger than ourselves. We're connected to the cosmos in fundamental ways. The atoms in our bodies came from stars. The forces that govern our cells are the same forces that govern galaxies. We're not separate from the universe, we're part of it. And maybe that's the real answer. Not whether we're in a black hole, but that we're here asking the question. That we're conscious, aware, curious beings trying to make sense of it all. That's remarkable, regardless of the cosmic context. So keep looking up, keep asking questions, keep wondering. The universe is vast and strange and beautiful, and we're lucky enough to be here, experiencing it, trying to understand it, if only for a brief moment in cosmic time. Thank you for joining me on this journey tonight. Whether we're inside a black hole or not, we're in this together, all of us on this small blue planet, looking out at the stars and wondering what it all means. Keep being curious, keep seeking truth, and remember, the best answer to a profound question is often another question. Until next time.